1, 2, 3, via. Buongiorno, benvenuti a questo.
Good afternoon, welcome to this conference. Once again, this year, we have the chance of hosting a high-level
Scoperta scientifica dell'anno. Forse davvero in questo caso possiamo dire una delle
contribution of one of the most important discoveries in the century, I would say.
l'universo non smette
The
mai di
universe
sorprendere.
never stops surprising us.
Noi che siamo
We are
interessati alla
interested
realtà
in
siamo
the
contenti di
reality in
sorprenderci.
all its aspects,
Siamo contenti di farci sorprendere.
and we're happy to be surprised by the
Anche quando
universe,
i segnali che ci
even when
arrivano
the
sono
signals
segnali
we
quasi
receive are
insensibili, come vedremo,
almost
al limite
imperceptible. They
dell'immaginabile,
are beyond the limits of what can be
perché
imagined,
anche segnali così
because also
deboli in
these
realtà
weak
possono in questa
signals
occasione
can
portare il segno di una cosa
bear the
grande.
signs of something
C'è un
much
bene
bigger.
per noi
There
anche in
is
questo
something good
dialogo
for us
con
also
questo
in this
mondo,
dialogue
quindi non
with
solo
this
per l'universo, che è la natura,
you are good for me,
l'universo
you as the
fisico che
universe, the
rivela
physical
qualcosa di profondo
universe that
e quasi
reveals the
celeste
deep order
attraverso segnali
through very
delicatissimi
delicate signs like
come
those we are
ultravioletto.
going to talk about
Sono
today.
passati esattamente 100 anni da quando Einstein ha
100
pubblicato le
years
teorie
ago,
della relatività
Einstein published
generale
his theory
e
of
proprio
general
quest'anno,
relativity.
11 febbraio,
This year, on
sono stati
February
pubblicati
the
dalla fondazione
11th, the
Ligo un
responsible
documento aperto e
of the
conosciutissimo
Ligo
a
communication,
modo di
we're going to talk about this,
apprendere. Hanno dato la
spread
notizia
the
che il
news
loro
that
strumento aveva
their
per la prima
instrument,
volta
for the first
spiegato
time
le onde
ever,
gravitazionali,
revealed
una prova
gravitational
bellissima e
waves.
importantissima per
This
sapere
is a
della
beautiful
relatività,
confirmation
che
of
ci insegna che
the
la gravità, questa cosa che ci
relativity
richiama
theory that
come
it tells us that gravity, which we feel even now sitting in
può
our
assumere la
chairs,
forma di
can
un'onda
take up the
con una luce invisibile
shape of a wave
che
like an invisible
rende
light
possibile il
that makes it
rapporto
possible for us to
cosa-tempo
have a relationship to things with the things that otherwise would
ed è
not be
veramente quello
within our
l'obiettivo
reach. So, as the
una
title
nuova
of this
finestra
conference
sull'universo.
says, this is a new window on the
E una
universe,
luce
a new
nuova
light.
per essere vista richiede degli occhi
If you
nuovi,
want to
degli
see a new
strumenti
light, you
nuovi.
need new eyes, new
Così si apre verso il
instruments.
futuro, i
So a,
nuovi
so
sviluppi
a
che
future
vedrà
of new
nuove tecnologie non
developments
solo da Terra ma anche dallo
opens up
spazio, come
with
sentiremo
technologies from
con
Earth and from the
programmi
space, with
ambiziosi
ambitious programs,
e è già in corso, in
some of which
collaborazione
have already
Italia è
started
prima.
with
Ma di cosa si tratta
Italy
questo
as a leading
grande,
partner.
grande
Our
ospite
hosts
di
today will
oggi?
really explain
Allora,
this to us.
innanzitutto
First of all, I'd like to
abbiamo l'onore di
introduce
avere con noi uno dei principali
one of the
responsatori
most
scientifici della
important
collaborazione
scientific
stellare, una protagonista spiccata di questa
stakeholder of
grande
the Ligo
scoperta è
Corporation,
Laura Cadonati.
Laura Cadonato. Laura works with astrophysics and gravitational waves. She has always had a leading role in this cooperation, not only in terms of the discovery of the waves, but also for the path that led to this discovery. She deals with characterization and interpretation of short-term gravitational waves that are produced by, for instance, black hole collisions, explosions of supernovas, and the like. She graduated in physics in Milan. Then she moved to the United States, where she got a PhD in Princeton. Then she went to MIT for a graduate, and she now teaches at the Georgia Institute of Technology in the United States. She is part of the American Physical Society, and she is the coordinator of the Gravity Working Group of the American Physical Society. She is responsible for the commission that follows the data analysis of Diagon. She has already been awarded a prize for her career, and she also has three children. Well,
E poi presenta anche il nostro altro speaker,
I'm going also to introduce
abbiamo con noi anche la persona che per
the man
professione è
who
scientifica
had
e
the
per specialità
scientific vision
biologa,
and the great responsibility,
è la persona che
and he is the
nell'intervista
one who, better
possa
than anyone
illuminarci
else,
alcuni
can
chissà che
show
cosa si
us the
aprirà per il
perspective
futuro
that
dei
this
nuovi
discovery
ragazzi
opens up for the future, for new
dell'Italia e del
generations.
nostro paese.
Roberto Battistoni.
Il suo campo di ricerca
His
è quello
research
di studio
field
della
is the
fisica
study of
quantistica,
fundamental physics through
specialmente con acceleratori di particelle
experiments with the
particolari,
particle
sia nel settore
accelerators as well as
spaziale
in the space
attraverso l'uso di gas
sector with the
fotosferiche a
measurement
microscopio,
of cosmic
in
rays
particolare
and
con le
particles.
tante cose che
So we don't have the time to list all the things he does,
Roberto ha
but he
guidato
was
in
also
Italia
led in
l'Organizzazione
Italy,
Spaziale
the
Italiana
Italian Space
e
Agency and
l'Organizzazione
the
Nucleare,
National Institute
avere
for
ruoli
Nuclear Physics.
nel progetto AMS,
In
che è
the
un laboratorio unitario
MS
dove
project,
studia diversi corpi
which
celestiali
is a
e
laboratory
anche
for the
elettrici.
study of
Nel 2011 questo strumento si
anti-mass.
trova
This
a
is
viaggiare
now in the International Space Station since 2011 and has provided us the most precise measurements in this sector, opening up or paving the way for new studies. He studied in Pisa and then in Paris. He taught in Perugia at the university, and since 2012 he's at the University of Trent. He wrote and he worked in the ISI, and since May 2014 is president of the Italian Space Agency, and he is the father of four children. And now I leave the floor to Laura. Thank you. First of all, I'd like to thank the organizers, and particularly Professor Bersanelli, for inviting me here. It is an honor for me to be here in Italy to present the work we do. You were talking about the discovery of gravitational waves, the collision of two black holes. This was a discovery that was announced in February, 100 years after the postulation of the existence of these waves by Einstein in the theory of general relativity. We then confirmed 2 months ago this discovery. Today I would like to start with an introduction on gravitational waves and on the importance of this discovery. Many scientists actually devoted their entire careers to this. We'll talk about what LIGO is, and we will talk about the perspectives for the future. Well, if you think to look at the sky in a clear night in the summer, this is actually a picture with an ultra deep field from the Hubble Space Telescope that is in the space since the 80s. In this image, you can actually see galaxies which are 10 billion light years away from us. this is a very precise image we can have in our with our eyes. The knowledge we have of the universe is based on electromagnetic waves, infrared, visible, X-rays, gamma rays, and great progresses were made since Galileo studied the skies. We now know that the universe is dynamic. There are stars exploding, galaxies that melt, and cataclysms that release enormous quantities of energy. And we know this because of electromagnetic waves. The gravity force shows how the stars moves in galaxies, how galaxies move and sometimes collide. There are a lot of questions that need still to be answered. What is this dark matter that we know is in the universe but we cannot see it? And what is inside the black holes? What are these black holes that Einstein told us about? And how do stars explode? What happened in the very first moment after the Big Bang? There are so many things we still don't know, and my co-workers, the whole scientific community wants to find the answers to all these questions. The gravity force is at the center of the relativity theory that was drawn up by Einstein 101 years ago. He was not satisfied with Newton's idea that two objects with a mass get attracted by the gravity force. This is something you learn when you go to high school, actually. And what is this force? This we do not learn at school. Where do this force come? Why do two masses attract each other? And what would happen if this force should disappear? We know we need 8 minutes to switch off the light of the sun. What was the message that actually gives us the information on what happens on planets and black holes? Einstein had a genial vision. He redefined gravity not as a mysterious force between two masses, but as a consequence of the fact that the space is not flat. It is not rigid, but it is distorted by objects with a big mass. What you see here is a representation, a two-dimension representation of space as Einstein saw it. You should imagine it as a plastic sheet, and the effects of stars and black holes is that they create these curves in space. Some of these objects, you can see them with their light. Others are dark, we cannot see them. If we look very carefully at the back, there is some kind of hole that is a black hole, and it is, so to speak, a place in the space that is so deep that light cannot come out of it. The reason why the Earth is attracted to the sun is because it moves on a curved space. And to quote John Wheeler, the matter deforms the space, and the curves of the space determine the matter itself. So it's a new definition, in a way, of Einstein's theory. And here we have the formulation of gravitational waves, which are changes, small waves in this tissue, in this network that is produced when there is a change in matter. So let's think about two black holes colliding. This is a big perturbation of space that gives way to waves. If we throw a stone in a lake, you see some waves that propagate. Well, the same things happens with the gravitational waves. There is a catastrophic event that releases a lot of energy, and this tissue, which is not rigid, makes this wave propagate at light speed. In 2016, we really saw these waves. We can see this, for instance, if you think about a fabric that curves, so the distance between 2 points changes. So that's how we can actually detect the passage of a gravitational wave. Then I will tell you how LIGO does this. But I want first to stress that when Einstein 100 years ago foresaw the existence of gravitational waves, he jotted down a few figures and decided that this effect is too small. It is not possible to measure such a small effect. It is not easy to deform space. Space is a rigid element anyway, and that's where he was wrong. Einstein said it is something we cannot measure, but well, now we can. On February the 11th, this is actually a video I wanted to show you to show how when we have two bodies rotating, they could be two black holes. By rotating, they change the way they deform the space around us. This is the first signal of production of gravitational waves. That is to say, the spiral movement of these two objects. You can see this wave that propagates from the center towards the external part. Now I'll show you a video, and it has to do with the with what we detected on February the 11th, 2016. My scientific team announced the discovery of gravitational waves, which were produced 1.3 billion years ago, when the first life forms were being created on Earth. So two black holes collided and exploded, and they released an enormous quantity of energy in the form of gravitational waves. This is a simulation that you see of the effect of distortion of light produced by stars that are behind the two black holes. So you see the two black holes that are getting closer. The stars do not move. There is no telescope that can actually register this effect, but we can see the production of gravitational waves. You see that green lines. This is a numerical simulation until the two burst, and they propagate in the universe, traveling at the speed of light, at light speed. On the 14th of September, this burst hit the Earth, changing it as in this simulation. So this is obviously an exaggerated effect. Here in Italy it was 11:50, and I don't think that you felt you were being compressed, because it is a very small effect. But before telling you how small it is, I want to talk to you about the LIGO. This is a picture of LIGO from an aerial picture. I think you can see it very well. You can find it on Google. LIGO is this L-shaped structure, 4 kilometers long. So let's see how it works. The basic idea is that there is a laser ray that is divided till it hits two mirrors, it rebounds and is recombined in the central mirror. What happens in terms of electromagnetic waves? We tune the tool so that the two, when the two recombine, the signals are cancelled. If the two arms are really not moving, we see. But if a gravitational wave is passing through, the two rays interfere in different ways, so we can see a bit of light in exiting from the tool, like in this image. So we concentrate on those lights, and this is how we see the relative change in the arm or in the two arms of the tool due to the passage of gravitational waves. Well, again, here the effect is really exaggerated. What we really see is the movement of this mirror, but it is a very small, small, small movement. There are so many things that move these mirror more than gravitational waves. Just to give you an idea, a scale, a proportion. Let's say this is an atom of nitrogen. You see the diameter in red of electron 10 times minus 10 meters. That's the electron moving and in the nitrogen atom. We are now zooming in, and this is even smaller, 10 times minus 11, so it is really small. So we really monitored the movement of these mirrors at the level of 1/1000th of the size of a proton. There are other effects of different kinds, but the Ligo technology is very important because it is a very precise tool. We have here two tools for the LIGO. On the American map, you see where they are. One is in Hanford in Washington, and then there is another one in Louisiana, in Livingston. So one is in the woods and the other one is in the desert, because you need to find places that are quiet and not too crowded. These two sites are 3,000 kilometers one from the other. Since gravitational waves travel at the speed of light, there are a maximum 10 seconds of delay between the arrival to the two different tools. All the other causes that can move the mirrors cannot be registered. It was built between 94 and the year 2000. We have the initial LIGO from 2000 to 2010. And then we had a series of upgrades. To build this kind of detector is something you can do only in cooperation. I'm a member of the LIGO Scientific Cooperation, which is a consortium of about 1,000 technicians, scientists, engineers, organized with different kinds of expertise, of skills. So there are people who are expert in sciences of materials, in electronics, data analysis, astrophysics, and each contributed their own skills. So we have 80 different institutes. So you see here the logos of the different institutes participating in the cooperation at world level, because there are 16 countries that are part of the Ligo scientific collaboration. So one of the reasons why I really enjoy being part of it is that starting from the vision of Einstein, the genius of one person who really could see something that no one else saw, 40 years ago, three scientists, Kip Thornbury, Wise, and Ron River, had the idea to create this detector. So they contributed their idea, and together with all the other scientists, with about 1,000 people who made this possible. This is a timeline of the first observing run in LIGO, advanced LIGO, from the 12th of September 2015 to the 19th of January 2016. The first event was on the 14th of September. We were not really ready, actually. This was just like actually switching on the tool and already capturing this first signal. Then there was another stronger event, and that was our Christmas present on December the 26th in Europe. But for us, it was still the evening of Christmas Day. So these were the two events which were really strong. I will show them to you later on. Then there was another event which was maybe less strong on the 12th of October, which we now call a candidate. Anyway, we recognized the signal of the collision of two black holes. This is the graph that comes from the article of the first announcement. This is the first event that led us to the discovery of gravitational waves. There are different elements in this graph. In the left column, we have the data of the Washington detector. On the right, you have the Livingstone data, the detector in Louisiana, in the woods. The first one was in the desert, as I was saying. The two signals you say in the first line are filtered data. That is to say, we just removed high and low frequencies, and we created a low band filter. What we saw with by naked eye, the signal that we can expect from the collision of two black holes. In the second line, you see the simulation of the numerical relativity of the aspect of this signal, and there is a signal that increases its frequency in time. That's when the two black holes are in this spiral, one around the other. And the higher the frequency of the signal, the closer are the black holes. And then one of the two black holes relaxes. If you look at the distance between the peaks, we actually estimated the parameters of these sources, so that is to say how big the black holes were, whereas they were rotating around themselves, and how close they were. The last plot, we have the data, we have the simulation, and then we have the difference between the data and the simulation. A match we can almost do without any other tool. And then we have a time frequency map with this chirp, this increase in time in the frequency that once again tells us that this is the signal expected for two black holes. The signal is consistent in the two detectors. If you look at the right column, the blue line is overlapping a blue line. So we have two signals with a distance of 7 seconds, but they have the same characteristics. So it is something that is a signal that is outside the detector. So it has an astrophysical nature. The frequency of these signals can be perceived by our ears. So what I would like to have you listen at the moment, if we take these signals I just show you, if we make it in a speaker, what happens? Because the frequency is the same that can be perceived by our ears. And I would like for you to listen to what these signals correspond for the two events in December and in September. And I will first show the frequency typical of the signal, and then, just to make it easier for you to hear it, in a frequency with a higher pitch. Let's listen. What you just heard is the latest cry, the last cry of two black holes which collided 1.3 billion years ago. So for the first time, we listen to the sound of the universe. And well, that's it, through inverted commas, because these are not acoustic waves, these are gravitational waves, and we opened up a new window on the universe. These signals bear information that is different from what we have. Electromagnetic waves tell us a few things about the universe, whereas gravitational waves give us a different meaning. The perception you have of reality comes from what you see and what you hear. We first looked at the universe, but now we can listen to it. So this is the beginning of a new way to study astrophysics. We also discovered that there are black holes that are 20 times bigger than the sun. We didn't know that. In this graph, you see in purple the size of black holes, which we knew on the basis of X-ray studies and electromagnetic waves. There was no evidence of the existence of black holes 20, 30, 60 times bigger than the sun. So these opened up a new exploration field. We now know of the existence of astrophysical objects which we didn't know for sure that existed. They have a spin, and we know how they can be produced. So this is again a new research field. Ligo is not the only project studying gravitational waves at the moment. Not too far from us, there is then another detector, which is Virgo, which is in Italy, near Pisa. We cooperate closely with the Pisa Center. We share research on instruments and materials, and we carry out data analysis together. So it's a unique collaboration. Virgo will start collecting data by the end of this year, and we really have the perspective of having three detectors, and I will then explain why this is important. Kagra is a detector in Japan, which is now at the building phase stage. We wait for it to, but we expect it to be part of our effort, maybe by 2019. Then there is another project for the creation of a detector in India, which would be part of the Ligo consortium, and that would take us by 2022-23 to have a network of 5 detectors. With the two detectors, we managed to see these signals. Now, with 5, we will be able to cover the sky widely, and we will be able to see where these events come from. So, in order to show this to you, I can show you that for these two
Quello che possiamo dire è su da
real events and the candidate. What can we say about what happens? The event of September comes from the southern hemisphere. If we take into account the arrival time of the two detectors, we can say where it comes from. So in this case, the southern hemisphere. So, well, this is as a shape of a banana because we just know that it comes from the southern, but it's not very precise. The event of the 26th December. Well, here the resolution is the blue one is not very well good, so we are well. There is a lot of uncertainty about this event. And again, the red one. If Virgo had been active at the time in autumn, these areas would be smaller. So for the G W1590914, the first, instead of a banana shape, we would have had a P. Why is this important? Is it important to know where these events come from? Because once we can determine their origin, we can work together with our colleagues of the electromagnetic field and with our astrophysical as astrophysics colleagues in what we use to call multi-messenger astronomy, so different messages then electromagnetic waves, neutrons, and different messengers that can provide us with different information on the universe that surrounds us. And there are other detectors working at different frequencies. So then Roberto Battistone will talk about Lisa and the possibility to research waves with for periods with well going from minute and hours. The We are actually working also on projects for longer times. If we could actually create the same results as last year, we talked about gravitational waves of billions of years. So we really hope to be able to have a spectrometer of gravitational waves, just like electromagnetic waves, with different frequencies and sources. And we could go back to the Big Bang. It is a very exciting area. This is just the beginning. This is not a final result, but rather a starting point. So I do hope that in the future one of my younger colleagues will be able to come here and talk to you about new discoveries with the gravitational waves. Good afternoon, everyone. It is a great pleasure for me to be here today. I would like to thank Marco and Laura for this very interesting presentation. What I will now tell you regards a different aspect of the same problem. Particularly, we are going to talk about what can be done in space. We saw the marvel of what it can be done on Earth, but now I would like to really take you to understand how gravity is. Can we have the sound? We can really say that gravity is meant to be studied in the space. And let's see what can be done. It is very possible to see what the Earth does. I'm sorry, but with the sound so high, the music so high, interpreters cannot possibly translate.
Non funziona? Ecco. La gravità.
Gravity is the most mysterious of all forces. Although it was the first to be formalized by Newton. And it is the only force of the four forces we know for which the principles of equivalence hold true. The gravitational charge equals the inertial mass of a body. If we take a bottle, for instance, an empty bottle, we throw it in the air, it falls in a certain way. If we do the same with a full bottle, well, if we leave them, they both fall in the same way. This happens because of gravity. If I did the same with an electric charge, it would have not have worked. If there's a body which has a stronger charge than the other, they would have had a completely different movements. So this gravity is the gravitational mass and the inertial mass seem magically to coincide. Then gravity is so weak that many precision tests have to be carried out in space. We really owe a lot to this guy who is here with his wife. That's Albert Einstein. As Laura said, he really changed the way we look at space and time. And he realized that if we try to explain time and space as a fabric that has been deformed, distorted by the presence of masses, we can actually magically understand a lot of things like the orbit of planets, gravitational masses, and many other things like black holes and many other aspects. So this is something, well, it is a space that can be distorted, where there are some connection between different distances. So it is completely different from what we were used to. How can we study gravity? As we said, these are very weak effects, and well, to work in space is extremely useful. We need to study the movement of masses that move freely within a gravitational field. To create a body that moves freely, it's not easy. It has to be a body in a free fall. It cannot be either supported nor touched, and it has to be shielded from any other forces like pressure, air, wind, radiations. Where can you find this? Where do bodies move freely? Obviously, in space, we see things magically floating. So that's where we can find free-falling bodies. But as you might say, this is a system where the gravity is acting anyway. But what is really a marvel is that when I freely fall, like the bottle I dropped, when the body drops, gravity actually disappears. So that's the principle that enabled Einstein to draw up this theory, his theory of relativity. The effect of gravity really disappears. If you have if you are overweight and you jump from up the stairs, if you have 10 seconds when you don't weigh anything. But so there's this moment during your fall when weight actually disappears. In order to do this, a free falling body needs to be protected also in space, also from the light, from pressure, from many other things that could actually disturb the free fall of this object. If you have a look at what happens to astronauts within a space shuttle, so let's look at this fairy who's positioning planets in an orbit where they float and they can freely fall. Nothing moves in a different way. This is a classical example of a free fall in gravity with a completely free movement, free from any other effect. These are the tools, the instruments we need to study the possible disturbances to gravity, like gravitational waves. But there is also another aspect. It's not only the particles, masses that can be used to study gravity, but also light can be used. For instance, the energy which equals a mass, when we have a photon moving in a gravity field, it has a gravitational attraction even though its mass is zero. So this is the picture I showed you at the beginning, and it is a very particular image because it shows what happens near a black hole. This is called Gargantua. It's the interstellar black hole. Moving in front of this black hole, we can see this incredible distortion of what is behind this black ball at the center, because this distorts the path of stars and it creates this incredible effect where while moving I can see what it's behind, but in a distorted way. This is something very scientific. The calculations were made by Kiptona, and as Laura was saying, it was one of those people who talked about Ligo, interference tools, and he will probably be awarded the Nobel Prize for that. So it is an extremely serious study. All this can be done with satellites that move within the solar system and that send out signals from the opposite side of the sun. The radio wave has a curved orbit when it moves from the satellite and the Earth. So when it moves behind the sun, we have this distortion of the radio wave sent by the satellite from the other side of the sun. If we use a very powerful telescope, a radio telescope, or using a probe, Cassini, that was built by the European Space Agency and the Italian Space Agency as well. So we saw the artificial light that was produced by an antenna built by men that was curved by the presence of the sun. This graph, I don't want to talk about the details, but this black line, and there is this dotted green line, which is the measure of this movement, and it is a very precise evidence of how the radio wave actually gets curved when it passes behind the sun. Now let's talk about the gravitational waves. What I've been showing you are actually static measurements with the gravitational field in static conditions. Gravitational waves are incredibly something that can change the space and time as if it was one of those jumping trampolines where children play. First of all, we need to bear in mind that there are some frequencies, that there is a duration for these phenomena. Let's take light first. Light is a unique phenomenon. It is described by a single equation that goes from radio waves up to microwaves and infrared, what we can see with our eyes, but then again also X-rays. So this is light. In order to look at it, it interacts in different ways with the matter, and it goes from radio waves from 1,000 oscillations per second up to billions of billions per second as for the gamma rays. So for gravitational waves, it is possible to analyze this phenomenon to see how rapidly it moves. Since they are produced by very big bodies, big stars and black holes, so they cannot actually move billions of times per second. So these phenomena are actually slower. You remember the signal captured by Ligo? It actually lasted like about half a second. There was this whistle that we could hear with our own ears. But gravitational waves exist also at lower frequencies. Laura talked about hours, years, billions of years. And if we think about gravitational waves as a slow phenomenon, we can say that you might remember the Ice Age Bradipo, these three-toed sloth, which was in the Ice Age, which was quite rapid in its movement, and then there was the other one in Zootropia. That was the one. That's the slower one. That's the one we have here as a comparison. So, well, these are stars annihilating in black holes, and a series of mechanisms. We are really opening up a big window on the universe. So, with the satellites moving outside the atmosphere, we have learned a lot about what it's surrounding us. Now we can go even beyond that. How can we measure the curve of the space-time curve? If I have an emitter emitting laser light, that's the one on the left, and which is detected by the receiver on the right. The space-time is this squared pattern that shows the same movement as it is emitted and received. So the receiver sees the same frequency that is emitted by the first of the 2 points. So if the distance changes, the receiver receives a distorted wave. The effect can be smaller, as we saw before. It can be really small. But, well, the principle is the same, because we are distorting the path of light, so we can actually make some observations by using lights that follow the propagation of the wave, and another one that moves perpendicularly, as Laura was showing us before. So we have created interferometers with arms of 3 to 4 kilometers, very sensitive. They can actually perceive the part of the nucleus of an atom, but there is also a margin of improvement for these tools in the future. But there's something incredible that can be done in space with an interferometer that has arms of billions of kilometers. So it's really an astonishing length. The moon is 400,000 kilometers from us. So an interferometer with arms of 5-7 billion kilometers can do something that goes beyond the distance between the Earth and the moon. This is, it's actually an empty space. I just needed to make sure that the satellite or the triangle are centered, and the reference bodies in free fall are actually, well, in a perfect free fall situation. That's what is more difficult. Once we have built this kind of interferometer, we can move also to detect a very low frequency, one swinging at the time at an hour. LISA is a project that is actually working on this. These are 3 satellites with arms of about 5 billion kilometers that rebound on reference masses in perfect free fall, which are protected by the satellites that shields them from the influence of the sun. And also in space, this effect is quite small. In order to detect swinging for very slow swinging, we need to have an instrument that can detect the movement of an atom. This is very sensitive because it's 5 million kilometers away within the gap of an hour, avoiding forces that cannot be heavier than a bacterium. So this LISA project works with this kind of a challenge, which is not different from that of interferometers on Earth, because we are on different frequencies and we are in space. This gravitational sensor in free fall is actually a cube made of platinum and gold. When we scientists like to, to use some link if possible. So, but these are actually substances that are extremely suitable for this. 10 centimeters each for each size, and once it is flying, the satellite moves around it in order to protect it from any external pressure. It doesn't touch it. It only avoids disturbance, apart from the laser light. And now look at this signal. It might seem the same one as before, but here we don't have half a second. We have a 4,000, 5,000 seconds, to say 1.5 hours. This interferometer can reach a scale of a phenomena which is completely different. It's like having an orchestra that's a violin and that is a trumpet. So this is completely different. So we need to have all the different frequencies that can be reached in space.
And when you explore outer space, you need to adapt because you cannot adopt the same strategies you would adopt on Earth. So once you have designed your experiment, it must work perfectly like clockwork orange. Like a clockwork, and so they are very delicate mechanisms. And before launching the LISA mission, we had the LISA Pathfinder, that was a test mission that was launched in December 2015 with one of the special tools created by the ESA. So it was something that took 15 years to be made. Actually, it's a laser arm that was sort of compacted in a 1 meter size with 2 reference masses with laser lights that reproduce just the speed of light and the distances in outer space. But when it comes to technology, the sensitivity, the delicate mechanisms, everything was tested thanks to this experiment. And the most important finding and outcome is that the sort of devices were improved. That was made by the ESA, by Europe, and the head of this mission is an Italian professor from Trento, Stefano Vitale, that was the head and coordinated this very important international project. And so this technology was validated in order to be used in the future. So in order to make these simple, allow me to say, tests, actually everything is very complicated. This is the satellite, this is the LISA Pathfinder. Before being put into a space simulator, ultra vacuum system, where the outer space settings are perfectly simulated in all condition, and the specific aspects have been studied for over 10 years. So all the specific spurious aspects. So fundamental research made other similar sectors go ahead because it was possible to make progress in other areas and domains that are connected to fundamental research. And then on December 3rd, 2015, with just a slight delay, the LISA Pathfinder was launched by the European base on the French Guiana territory, and it was launched almost 100 years later after the fundamental work of Einstein on universal gravitation. So again, already Einstein had already done a lot on gravitation, but it took us another 100 years to make his study go ahead. So probably Einstein could have helped us a bit because he designed such complicated theories that it took us 100 years to sort of fully understand them and test them and put them into practice. So these years were very important from the Ligo discovery to the LISA Pathfinder positivity test. We were able really to make huge progress in this sector. So now we are getting closer to a new gravitational astronomy, a new era for this discipline. So we are convinced that this is going to mark a major step in the evolution of these disciplines. And so we're going to go ahead and discover much more about the colors, the sounds of gravitational waves that are going to allow us to see what is now invisible. The black holes, that are these hidden giants at the center of galaxies, are usually hidden and masked and veiled by dust, other stars, other phenomena that do not let us see them and watch them properly. On the contrary, in terms of gravitational waves, they are naked, but they are hidden by light. So that's why we're so excited and so happy about what has happened so far, because this opens up a new range of possibilities in terms of scientific research. So certainly in the future we're going to get great results in order to better understand how our universe is made. Thank you.
Sentite, io approfitterei.
Right, I would like to take advantage of these great guests for some more time. We'd like to ask a question to both Laura and Roberto. Well, I think we could really feel and sort of perceive with our eyes and ears the energy and the passion of these scientists, how much they want to better understand reality. So they're really eager to get a better understanding of the phenomena surrounding us. So I would like to ask them as a scientist, but also as individuals, as people, I would like to know what has been supporting and feeding literally your passion over the years. There are many young people in the audience. Maybe some of these youngsters are asking themselves questions about their future. Maybe some of them like these topics, like these issues. What would you like to tell them about, passion and keep doing what you like? Well, as far as I'm concerned, I can simply share my own personal experience. One of the things I've always felt very proud of as Italian is the heritage of Galileo and Leonardo. Being moved by curiosity, really wanting to understand things in order to increase the level of knowledge we have, in order to better understand who we are, where do we come from, and where we're getting to. This is what really kept me going in the past, especially when I left Italy. Because we are always scared of the unknown, we are always scared of change or what we do not know. But on the other hand, this willingness and wish to know, understand, study, learn, that's what supported me over the years. So I really kept sort of trying, and I think that humankind should always be driven by this desire to learn and improve and know more. And secondly, collaboration was another key aspect, especially when I was the most scared and frightened and felt a bit alone. I was really very much supported by friends, colleagues, mates. So collaborators played a key role. The fact of sharing a goal and being part of a team was very important for me. And I was very lucky because my family could support me somehow materially. I was also supported by many other people all around me. And I was very lucky. But then curiosity is a very light piece of baggage. So it's worth being curious and trying to go ahead in your life thanks to curiosity and passion. Roberto, what can you tell us? Well, I think that when it comes to curiosity, well, it's a great gift being curious. So if a person is curious and really wants to make the most of this curiosity and try to use it at best, well, then science is the ideal domain to make the most of curiosity. Because when it comes to science, you can really work on finding answers of different kinds, fascinating answers, charming answers. That's all about it. Nobody's going to get to happiness or get rich through science, because usually scientists make huge sacrifice, usually work in hidden places. Sometimes their work is not even known. Sometimes they are not known, but they really try to find answers to questions that made them curious for certain amount of time. It's about staying hungry, being curious, always having new goals, setting new goals and objectives. And science is really the ideal thing to cope with in order to stay hungry. So for those who feel these stay hungry feeling, so just don't give up. You need to find good masters, good teachers. This is very important. This is paramount, because maybe when you are a young lad, or maybe when you are a university student, you come across inspirational people that can really make you understand what you want to do in your life. So stay hungry, find good masters and good teachers, and always try to sort of set very demanding purposes. Science is not like sport. It's not important to join. You should win. I mean, winning is important. And so you should always try to strive for the best. So always try to rank among the first. This should be your main goal, trying to get to the best universities, the best results with the best people. And the Italian academic world is pretty good on an average. Investments are there, good brains are there, especially in the space sector. Italy is investing a lot at several levels, national and international. There are scattered experiences. I mean, there's the CERN in Geneva, then there's the European Space Agency, then Italy has special relations with the NASA. Again, there are many positive things in Italy when it comes to this sector, but on the other hand, there are still many difficulties. Not all our young, talented people can find their way in our country and have to go abroad, but we hope to change things in the future. But that should not be a limit. I mean, if you want to embark in this pathway, please do not refrain yourselves from doing so. I mean, what I can tell you for sure is that you should be driven by your curiosity, your passion. This is extremely important because it's going to make you go on over time. So with tenacity and effort and work and good teachers, you can really get very, very good results and make it. Well, I think you had the privilege to listen to the words of two excellent teachers and masters, and I hope they opened up your mind a bit and made me understand the importance of curiosity. That is a great gift. And I hope they were able to make you understand to what extent collaboration and teamwork are key to get to such remarkable results. The universe never stops surprising us. We saw it, we heard it, we touched it from a close. And in particular, I was struck by something. The universe surprised us, not just because we saw unexpected things, but because we're able finally to find an answer to a question that had been there for 1 century. And sometimes the answers that are the most surprising are those that have been so much awaited for. It's a dramatic dialogue with nature that we're experiencing. And this is about being curious. This is about wanting to get more knowledge. When physics make experiments, actually they question reality, but then they're waiting for the answer. It's not up to us to decide when the answer is going to come, because we did not make the universe. We're not the universe makers. But then, as in this case, well, when you get a hint of the result, really you get the feeling of getting to know something so important. And so this is a great privilege when you have the opportunity to discover something that was there but was almost invisible. Chandrasekhar said something I really like. It was Nobel Prize winner. He studied these compact objects that now can be seen through gravitational waves. He said once, somehow, oddly enough, any fact, any new perception I had never gave me the impression of being my own discovery. On the contrary, I had the impression to come across something that had always been there and that I had just had the chance to find. So this is the way it feels encounters with reality and nature can happen. So again, it's not about getting a whole picture, not at all. We're just at the very beginning. We are just at the start of a great new era. But then something new happens because you sort of get in touch with something that had been unknown for such a long time, and this makes us feel grateful and positive and confident. So thank you, and we're very grateful to our great speakers and guests. Thank you.